Okay, last chance for the code. Everybody get it? Everybody get it? Okay. All right. Let's get started. So 2.1, the homework assignment that was due today, that was probably a slight step up in challenge. You're going to get another somewhat related assignment that gives you a little bit of practice on that today, due Friday. And then afterwards, what we will do is we will look at a different way of adding vectors that's a little bit more systematic and can much more easily handle multiple vectors. And I might talk a little bit about that today just to sort of set the stage. Okay, in terms of logistics, so I went ahead and uploaded the attendance grades from the last lecture. They are done. Homework 1.2 is graded, and the solution should be posted. If it's not available, I'll make sure it's available for access after class. And again, 2.1 is due today. I'll tell you, if anything, one of the most common questions I got about the homework assignment via email was not about the problem, but about where it is in the textbook. I know that there was a couple people that had trouble finding it. So in this textbook, there are homework problems after every section, not just at the end of the chapter, right? And more often than not, the homework problems that we assign or that I assign this semester will be after each section. So like right now, we're in the first section of the textbook, section 2.1, so those problems are there. But one other thing that this made me realize is that I want to make sure that everybody is at least somewhat regularly checking the Teams channel, because the homework assignment out of the textbook was posted to the Teams, and I've decided that for the remainder of this week, so for homework 2.2 and homework 2.3, I am going to go ahead and post, in addition to the PDF on Blackboard, I'm going to post the screenshot from the textbook and the text for the problem, because I know that there's a couple people here and there that are waiting for their book to come via the mail, like they ordered it and they're still waiting on it. So I figure this week I'll go ahead and post the assignments. I probably won't do so after this week, but I understand that it's not your fault if there's a delay with UPS or FedEx or something like that. But yeah, make sure that you're regularly checking the Teams channel. One of the things that is very common that I will do on the Teams channel in this class is, so let's say we have a homework assignment and I'm getting a lot of common questions about one thing, like, oh, I don't understand this distance, or I don't understand how this moment is computed, or what have you. And what I might do, because it's a little bit more convenient, is I might just make a post on the Teams channel for everybody to see, so that everybody gets the hint on the homework, as it were. So if I have hints for given assignments, more often than not, I'll just post them directly to the Teams. Okay, any questions? All right, so what we're going to do is we're going to have an additional example on the whole concept of trigonometrically or graphically adding vectors, and then I'm probably going to introduce this more systematic means of going about adding vectors, and that's through expressing them in IJK notation. So just to recap from Monday, and just to make sure that everybody understands some basic terminology and some basic ideas. And I do this, one, because it's important. Two, if I'm being a little utilitarian, this is the type of stuff I may ask you on a celebration of learning. Whenever we have an exam in one of my classes, it's usually a combination of both computational problems, where I'm giving you, something akin to a homework problem, or some other question that involves math or some degree of calculation. But then I also give you some conceptual problems, where I will ask you I don't want to say open-ended question, but I may ask you something about a concept or something about a term. And so I want to make sure that you understand, the concepts as well. So I just want to make sure everybody knows the difference between a scalar and a vector. So scalars are mathematical objects that contain magnitude. So we're really just talking about plain numbers with scalars. But scalars can also represent real-world quantities, things like time, things like mass, things like volume, and what have you. But what we're primarily concerned with in this course are vectors. And vectors are mathematical expressions that contain both a magnitude and a direction. So physical representations of that might be velocity, acceleration, and most importantly to us, forces. Now, in terms of manipulating vectors, so we can change the scale of a vector by multiplying it by a scalar. That's where the term comes from. So if we multiply a vector by a scalar, what it will do is change its magnitude. It'll make it longer or shorter. But if we multiply by a negative number, it will flip the direction. It won't rotate the vector, but it'll flip it about the same line of action. So if you have a 20-pound vector like this and you multiply it by -3, it becomes a 60-pound vector just going in the opposite direction. Now, when we add vectors, the concept is that it follows a tip-to-tail fashion. So if I had a particle, and that particle had, let's say, 3 vectors on it, so a P, a Q, and an S, the idea is that graphically I would take those vectors and start stacking them in a tip-to-tail fashion, and the sum of those vectors would just be from the place I started to the end of the last one. And that's how we do it graphically, and that's how we've been doing it trigonometrically so far. I've got one more example just to sort of hit home the concept, as it were. But what we're going to find, and I think this is probably pretty clear already, imagine if we had to do just this problem using the approaches that we did in the last homework assignment. So we'd have to deal with P and Q first, right? We'd have to use the laws of sines and cosines to take P and Q and turn it into this. Then now we have a whole nother triangle. So we'd have this intermediate sum, we have S, and then we'd have another triangle to solve another set of laws and of sines and cosines to get to the final answer. So I guess the point is, what if I have a particle that has 6 or 7 forces going through it? That would just be a pain, wouldn't it, to do via a trigonometric method. Now, I think that those trigonometric methods are important for understanding the concepts, but as you'll see, there are some more efficient ways that we can go about this. Okay, so what we're going to do today, and I swear I don't think this computer for Windows 11 likes my terminology here, or my symbols here for my slides. Maybe I'll pull this up in a PDF whenever I get a chance. But what we're going to be doing is a vector addition example, and specifically what we're doing is solving for unknowns. So what I basically want is this answer. I'm looking for the tension in a given rope, so I want its magnitude and its direction. But let's talk about the scenario. So I have a vehicle here that's being yanked on by 2 ropes, okay? Now I've got one rope over here, and it is pulling at an angle of 30 degrees from the center axis of the car, and it's yanking on it with a force of 3 kilonewtons. Okay? Now I've got somebody else over here that they're yanking on it some degree downward, right? So 30 degrees here, some angle here, and some force here. Now the goal is I have one person yanking on it with a known force and a known orientation. I want to know what this magnitude and this orientation needs to be such that the resultant is horizontal, okay? And specifically horizontal with a magnitude of 4.8 kilonewtons. Now I think that kind of makes sense. I mean, if you have a car that's stuck, right, and you're yanking on it, the goal would be for the car to move this way, right? So the idea is I know this force, okay? What does this force and angle need to be to yank it with a net resultant horizontal force? Okay, does that make sense? Now, what I could do, now I want to make sure conceptually that this makes sense. Now, think about this. Let's use some common sense. I've got 3 kilonewtons being pulled at a angle of 30 degrees. Would you agree that if I pulled with 3 kilonewtons at an angle of 30 degrees this way, that the net resultant force would be horizontal? Right? It'd be symmetric. The problem is it might not be enough because I need 4.8 kilonewtons. Okay? That's how much I need to get the car to start moving. So I need to figure out what the magnitude and the orientation is, not just to get a horizontal resultant, but a horizontal resultant with that given angle. Hence why we're going to have another one of the odd triangles that we need laws of sines and cosines and what have you. Make sense? All right, so let me pull up the notebook and let's see what we can start working on. All right, so let me pull this out. All right, so let's take a look at this car a little bit and let's see what we can figure out. Okay, now I want to see if I can start identifying some of these forces and some of these components. Let's start off with, let's just describe some of these. So again, I'm going to start using some of this vector notation that we've been dealing with so far, and we're just starting to get used to. So let's first off start talking about this vector AB, okay? And what I'm talking about AB is I'm talking about the force and orientation for this rope. And I'm using the letter T because I'm trying to express how much tension is in the rope, okay? So the tension in AB, again represented by a vector, is going to be represented something like this. 3 kilonewtons at 30 degrees. Would that be a fair statement? Just to make sure everybody's okay with that. Now, this is, so far right now, our only means of expressing vectors. So we say a magnitude and a direction. It's kind of akin to polar coordinates, right? Now, later on, we're going to come up with a much more systematic means of expressing vectors. And I don't know, has anybody ever yet dealt with IJK notation or IJ notation? Some of you have seen that. Okay, so what we're going to do is we're going to take this vector TAB here in the not too distant future, and we're going to say it's so much I plus so much J. And so that'll be coming very, very shortly. But for now, I'm just sort of expressing this in a graphical fashion. Now, our goal for this problem is to figure out what the tension in AC needs to be and what that angle needs to be. But we know what our end goal wants to be. We know what the resultant needs to be. So what does the resultant need to be? Well, we know that the magnitude is going to be 4.8 kilonewtons. And if we want to talk about the angle, so from the horizontal, what is that angle going to be? 0. We know that's going to be 0 because it's horizontal. So let's draw this out. Let's draw this in a graphical representation like we've done before. So let's see what we can do here. All right, graphical representation. So we're going to start off with point A. So we'll put a point A right here. So we'll call this point A. And we're going to stack on here our first vector. Okay. Now I'm going to draw this vector something about like that. Okay. So we'll say that the magnitude of that vector is 3 kilonewtons. Okay. And in terms of angles, what we're talking about, that angle being 30 degrees. Fair statement? All right. Now what I'm going to do is I'm going to place a similar coordinate system right here. And I'm going to start drawing vector AC. Okay? Now, I don't know how long vector AC is. I have no idea. Okay? But let's see what I can see. And say, that's probably pretty good. Okay. Now I know that I don't know what that orientation is yet, but I know that when it's all said and done, the resultant is going to look something like this. And so the magnitude of that resultant is 4.8 kilonewtons. Now, so that I have it here, let's go ahead and draw the coordinate system here. Let's go ahead and draw that. So that we have that. Okay, is this fair so far? This isn't too hard, right? Okay. So let's go off our diagram up here and let's look at this. So let's look at alpha. Okay, because I've got 30 degrees here. I've got the magnitude of this. I haven't put alpha. Where do I put alpha here on this diagram? Well, I've got alpha as being this angle. So here's the horizontal coming down to AC. So I think that that's that angle, that's alpha. But if this angle is alpha, is there another angle related to the triangle that I can label as alpha right now? This angle right here, right? Because this angle right here is also alpha. I mean, right? So, because what we've got is we've got two parallel lines cut by a transversal, so that angle and that angle are equal, right? Because this green dashed line is parallel to that one, and that's the line. So far, so good? In fact, if I go back up here, let's look at the answer here. This is what we're after, right? So I need this magnitude coming down. I need this. Isn't this just alpha? This part right here? I think it is, right? Because we're trying to find the magnitude of AC. That's really what we're after. So I think what we can do is we can say it's some magnitude, but that's just alpha. Now, I don't know about you, but I think this is a pretty doable triangle now. So let's handle this like we've handled all the problems up until now. So I've got a triangle. I have three known quantities, this side, this side. So normally we would be solving for the resultant. In this case, we're not. We're solving for one of the unknown components. But I know the magnitude of that resultant's got to be 4.8. So I know this side, and I know this angle. So this magnitude, if I wanted to solve for that magnitude, what do I do? What law do I employ? The law of sines or the law of cosines? Cosines, right? Because the law of cosines is most readily usable when all the information is hugged onto one side, two sides, and the angle in between. So what we can do is we can start by determining magnitude of TAC. And I'm going to do that using the law of cosines. So the magnitude of TAC, which again, I can also just call that TAC without the little arrow over it. So I'll probably just do that in the formula. So how am I going to do that? What's the law of cosine say? It's that squared plus that squared minus 2 times this cosine of that. Is that right? So as a big formula, that would be TAB squared plus R squared minus 2 TAB R 30 degrees. I think that's right, isn't it? So that's 3 kilonewtons squared plus, let's see, 4.8 kilonewtons squared minus 2 times 3 kilonewtons, 4.8 kilonewtons, 30 degrees. What do we got for that? Say it again. 13.5. You take the square root? 2.66. Do I have a second on that? That's what I got 2.66. I would check your exponents and see if you took the square root of the whole thing. Because I got 2.66 kilonewtons as well. Yeah, so that's got to be squared. That's got to be squared. Nothing else is. That's a minus, and don't forget the 2 in front of it. You got it? Yeah. Okay. Everybody else got that? Okay, so we know the magnitude. Now the only thing left to do is solve for alpha. So let's see. Here's alpha. I know a pair of opposites, right? Because I know this angle and the length of this side. Why don't I just use the law of sines? So we'll say the direction of so the sine of alpha over 3 kilonewtons is going to be the sine of 30 degrees over 2.66 kilonewtons, right? Because we've got the sine of this angle over this, right? The sine of this over that, and that's this magnitude, equals the sine of alpha over 3. And we're ultimately after alpha. So all we've got to do is take this, multiply it over, take an inverse sine, and I think we're rocking and rolling. So let's see. Alpha equals sine inverse of that. Oh. And what do we have for an angular measurement on that? We'll say like to the nearest tenth of a degree. We don't need to get too specific here in class. Anybody have an answer for this one? 34.3. Do I have a second? Awesome. So what is TAC? It is 2.66 kilonewtons at an angle of 34.3 degrees. All right. Let me take a step back and see if anybody has any questions on this. Not too bad, right? Hopefully after the last assignment, this should be pretty straightforward. Sound good? Okay. Now, I do want to introduce the idea of the IJK notation. If you've seen it before, then this should be a refresher. If not, this is brand new. But I don't think it's going to be too terribly difficult. But we're not going to get into our examples because we're going to save that for Friday and whatnot. Okay. So just to give you kind of an idea of what's going to happen, I know I'm skipping ahead to lecture 6, but I just want to kind of introduce the idea of IJK notation. For the first little bit, we're only going to deal with 2D vectors, and then we'll extend this into 3D. So I think by now, I think we understand the idea that a vector needs to be able to express both a magnitude and a direction. Okay, but what's also most important is that we can recognize that vectors can be split up into a sort of tip-to-tail fashion. And so what I mean by split up is this. Here's what I mean, okay? So if I have, let's say, these 3 vectors, right? These 3 vectors. If I wanted to add them up, what I would do is I would stack them in this tip-to-tail fashion, this to this to this, and just trace a line from beginning to end. But on the flip side, think about it this way. So if I take P and I take Q and I add them up, I get this. I could also take this vector and split it up into 2 different ones, as long as from tip to tail, I got from beginning to end. So what that means for trying to standardize this process a bit is, what if I took vectors and I split them into X and Y components? So for every vector I ever define, instead of just dealing with this vector at some random odd angle, what I would do is I would say this vector equals some vector along the x-axis plus some vector along the y-axis. Okay? And I do that for every vector that I ever define. So a very useful way of splitting up a vector is into its x and y components. Okay? The cool thing about that is, remember, if you have vectors that are all along the same line of action, all along the same direction, I can just add up their magnitudes, and it's a lot more systematic. Okay? The convenience of using the x and y coordinate system is I can develop a pretty standardized means of defining every vector as in terms of their x and y components. Now, so what we do, so here's how this is going to work. Let's say I have a problem like this. This has 3 vectors on it. It could be 4 vectors, it could be 27 vectors, it could be what have you. Now, up until now, what we would do is we would take these vectors and deal with them 2 at a time. Take vector 1 plus vector 2, stack them tip to tail, we have a triangle, solve for the resultant, and then take that resultant, go to the 3rd vector. The resultant to the 3rd vector gets me a new resultant. Take that resultant, go to the 4th vector. And I keep going on and on and on and on until I've exhausted all of my vectors. But that just takes forever. The amount of computations just adds up. The room for error just adds up. It's not very efficient. Instead, what we're going to do is we're going to use these x and y components. So for example, this vector P, I'm going to split it up into some component along the x-axis and some component along the y-axis. Vector Q, some component along the x, some component along the y. So one thing to keep in mind is that as we start doing this, you do need to take care of not just the x and y components, but the signs of those x and y components. So for example, vector P is going to have a positive component in the x-axis and a positive component in the y-axis, whereas vector Q is going to have a positive component in the x-axis, but a negative component in the y-axis. Right? You've got to make sure that you're accounting for your signs properly. But once you've done that, all we do is we take all the x components, add them together, all the y components, add them together, and now we have a resultant. It's a lot more systematic, a lot more straightforward. Now, in order to do this a little bit more systematically, and in order to simplify our notation a little bit and standardize our notation, we go back to the definition of a vector. What was a vector? A vector is an object that contains magnitude and direction, okay? Right? So what we're going to do is we're going to start to try and separate those out. What I mean by that is, let's say you have some vector and it's got a magnitude F and some orientation. We'll define that orientation by some angle, theta. Okay. What I could do is I could say, well, instead of having the vector of magnitude F and the angle of orientation theta, what I'll do is I'll factor that F out. Okay? So I'll have the magnitude over here on the outside, and now I've got a vector, but its length is 1. Its magnitude is 1. Okay? We're going to start dealing with this concept quite a bit when we start looking at directions in 2D and 3D. But what we're talking about is the definition of a unit vector. So a unit vector is basically our mathematical means of separating out magnitude and direction. So think of a unit vector as a vector that has baked into it only direction. We factor the magnitude out. Okay? So if another mathematical definition would be any vector with a length of 1 or a magnitude of 1. Okay? Unit vectors are going to form very, very useful tools for us later down the road. Now, among the most common unit vectors that we deal with are our essential basis vectors, I, J, K. Okay? And this is something I have a feeling a lot of you are familiar with. Am I correct? Okay. So I, J, K are unit vectors. They have a length of 1, and all they do is express direction. Okay? So I is the unit vector along the x-axis. J, the unit vector along the y-axis. K, the unit vector along the z-axis. We tend to use IJK instead of, X, Y, and Z because we want to differentiate what are the axes of our coordinate system and what are our vector components. And I think industry standard, as it were, has settled on utilizing IJK because when we, for those of you that had seen it before, the moment I say IJK, you know what I'm talking about, right? You know I'm talking about vectors. You know I'm talking about dot products and cross products and things like that. If you haven't seen IJK yet, that's something we're going to talk about later in this course. But that's why we use the letters IJK, is it's very instantly recognizable. So the idea is we're going to utilize these unit vectors as a standard means of expressing vectors of any magnitude and any orientation. We're going to start off in this class with 2D problems, so we're only going to have I and J. If you understand how to deal with vectors in 2 dimensions, vectors in 3 dimensions are really no more complicated, no more conceptually difficult. That is also one of the benefits of expressing vectors in IJK notation, is that 2D and 3D don't really become any more or less difficult. Okay? Now, I will admit that 3D problems can get longer. They don't get harder, they don't get more difficult, they just take up more sheets of paper in your notebook because the formulas just get longer, the calculations get longer. But they're actually, from a difficulty standpoint, no more or less difficult. Probably the hardest part of 3D problems is just looking at the diagram and figuring out, okay, how far along you're going on the x-axis, how far you're going along the y, how far you're going up on the z. It almost feels like a homework assignment in Engineering 102 or ME 102 more than it is a statics homework assignment. Once you figure out that base stuff, the rest of the problem becomes very rote, and that'll become clear as we get into those topics. So what we do for notation is we say, okay, we kind of understand generally how this concept works, where we'll take a vector, split it up into its x and y components, and then we just add up those components individually. But in terms of actually expressing the vector, we use ij and k if we were dealing in 3 dimensions. So the idea is that, like right here, see how I'm taking a vector and I'm expressing it in, here's the component along the x-axis plus here's the component along the y-axis. Well, normally the way I would write that is I would say however much magnitude along the x-axis times I plus however much magnitude I have along the j or the y-axis times j. Okay, so I being that means of expressing direction along the x-axis, and j that means of expressing magnitude along the y-axis. Yes, I corresponds with the x-axis, J corresponds with the y-axis. Now, I have this formula here that is a straightforward means of taking a vector and plug and chugging. So if I give you vector f and I give you this angle theta, you can express this in IJ notation in a very plug and chug fashion with this formula. But I do have a note here. I want to make sure that you're very careful about this formula here. That what I don't want to have happen is you're doing a homework assignment and you just blindly use this formula and you get points taken off. And it's, but Dr. Mike said that's the formula on the slides. Just make sure that you're using the appropriate context. As an example, if the angle is measured from the y-axis, that formula doesn't work. You have to flip your sines and cosines. So just make sure that you're, observing what's going on. I mean, ultimately, you're going to use sines and cosines to split the vector in the x and y components. Just make sure that you're handling things properly. Either the angle is measured from the x-axis, or if it's measured from the y-axis, you're flipping your trig functions. So, make sense? Okay. So what we're going to do, and we're going to do this on Friday, we're not going to do this today, is I'm going to give you a vector, and I just want to practice taking a vector and expressing it in IJ notation. I just want to make sure that we're comfortable with that. Then what we're going to do is we're going to take a problem that has more than two components, and we are going to add these vectors together. We're going to do this on Friday. This is going to be infinitely easier than the laws of sines, laws of cosines, math that we're doing so far. If anything, those graphical and trigonometric assignments that we're doing now are intended to reinforce the understanding and the concepts, but beyond that, we're going to roll up our sleeves and start to do it this way. So this will be the last law of sines, law of cosines homework that you have in this class. So hopefully that is a yay moment. All right. Any questions? So I'm actually, again, letting you out a little early today. I'm going to pull up the QR code. One thing I will say, again, starting now, I'm going to start to count people late if they're coming in late. So I'll have to start doing that. But other than that, that's all I've got. I will see you all on Friday.